Assalamu alaikum. Welcome to lecture 5 of chapter 6. We are still in mechanical properties of metals. It's a rather long chapter because it covers a lot of properties. We will of course review what we did in the last lecture, and then today's lecture we will continue with plastic deformation of polycrystalline metals. We left with Hall-Pech equation. We will complete the discussion. Then we will go to effect of plastic deformation on grains, effect of cold work on strength, and solid solution strengthening. Towards the end, we will be doing effect of heat treatment on strength. So let us see very quickly review what we covered last time. We defined and explained resilience. Then we defined toughness, the area under the whole stress strain curve. Then we talked of toughness and impact testing. What is impact loading? What is toughness? What is impact toughness? What is the Sharpie impact test, the Sharpie V-notch test, and the machine? The procedure for the test with the Sharpie sample and the ISOT sample. We showed you a schematic diagram of the Sharpie impact testing machine. Another diagram where we showed the machine and the height h and h dash and the Sharpie sample and the ISOT sample, and how the energy is calculated during the test. Then we told you about ductile to brittle transition. There are high strength materials which have low impact energy. There are FCC metals which have high impact energy, and there are BCC metals which have high impact energy at room temperature and so on. But if you reduce the temperature to near zero or below, then they go through a transition from ductile to brittle behavior. This covered the initial part of tensile related properties and so on. Then we talked of hardness and hardness testing. How do we define hardness? What is the difference between hardness and strength? How do we do the test? We explained how we do the test by doing indentation. At the bottom of the page, we showed you some natural materials in terms of increasing hardness. We showed you the actual picture of a Rockwell hardness testing machine. And then we discussed the 4 different testing methods and machines: Brinell, Vickers, Knoop, and Rockwell, and the type of indenters and how we calculate the forces and the diameters and so on. We told you that section 6.5 will not be covered, and the next section is plastic deformation of polycrystalline metals, where the first topic was effect of grain boundaries on strength. Then we showed you the strength of a polycrystalline metal and a single crystal metal. We started talking of the Hall-Pech equation, where yield strength can be defined in terms of the average grain diameter. So this was where we stopped last time. Now let us start today's lecture. So this is your Hall-Pech equation. This is a relationship between strength and grain size, and it's a very, very important thing. And we have already said last time, Hall-Pech equation, the 2 scientists who discovered this phenomenon, Hall and Pech, so named together after them, Hall-Pech equation. Sigma y is equal to sigma naught plus k upon root d. Sigma y is the yield strength of the material, and this small d is the average grain diameter. Sigma naught and k are constants for a material. So you see, remember when we were talking of the effect of grain size on the strength of a material earlier, effect of grain size on the strength of a material, then we told you that if we reduce the grain size, if you have fine grains in the material, right, fine grains in the material, then there are lots of grain boundaries, isn't it? If the grain size is large, then there will be a few grains, so the boundaries between the grains will be a few. But if the grain size is very small, then there will be thousands and millions of grains, and each grain is touching the other on the grain boundary. So the grain boundaries, the amount of grain boundaries will be very big. And we told you that grain boundaries resist deformation. When you try to apply force and try to deform the material, grain boundaries resist that. So because of the presence of grain boundaries, the material has more resistance to deformation, which means that the material is stronger. So this is what we told you earlier in the relationship of grain size, which we can see under a microscope, to the strength of the material. So now here is an actual mathematical relationship to explain that behavior. You see, this is the yield strength of the material, and this is the average grain dia. Average grain diameter, because you see there are millions of grains. So when you see it under a microscope with a large amount of enlargement, then you can see the grains, and you can count the number of grains, and you can see the grain boundary. So all the grains will not be of the same dia, they will be of slightly varying diameters. So if you take the average grain diameter that you see under the microscope, then you put them here. And what is the relationship? These two are constants. So yield strength is inversely proportional to the root of the dia, isn't it? And if you remove these constants, and you square the two sides, then the grain dia will be inversely proportional to a square of the strength. So if you decrease the dia, the yield strength increases, right? So this is a mathematical relationship. This is very powerful because all science is based on this type of a discovery and so on, that you physically discover that refining the grain size will increase the strength, and you do it for 1 metal, 2 metal, 3 metal, 4 metal, and so on. And then some scientists try to come up with a mathematical model for this. So this is called a Hall-Pech equation. And for example, we will show you table 6.5 soon. For example, for mild steel, which is a very common steel used in all structures and so on, the value of sigma naught is 70 megapascal, the value of K is 0.74 megapascal per meter square, and so on. So these are constant values. These are like material properties. So if the Hall-Pech equation study has been done for any metal, like mild steel here, then by repeated experiments we can find the values of these two constants. If these two constants are known, then we can now predict that give me the average grain dia that you see under the microscope, and I can give you the yield strength of the material. This is brilliant. This is brilliant that you see, while making the metal, we melt the whole metal, we solidify it, slowly cool it, and then by the cooling rate that we use and so on, the same metal has different types of grain sizes. So if we can control the grain size, then we can control the yield strength of the material. So finally, yield strength increases with decreasing grain diameter, and there is a significant change in the strength with grain size refinement. We are just saying similar relationship between hardness and grain size. Hardness and grain size. We have told you repeatedly that if you increase the strength of a metal, its hardness also increases, right? Strength and hardness are two very different things, but if you increase the strength, the hardness also increases. So if by decreasing the grain size, the yield strength increases, then the hardness of the material also increases.